I'm going to speak about the update of a Hotfield network, the classical Hotfield network. And let me open this. Okay. Can you see my slide, my screen?
Yes.
Great. Okay. So in order to retrieve something from the network, we use a process that converges to a fixed point. So what I need to convince us is that the process of retrieval is going to converge to a fixed point. The way I'm going to do this is by showing two things. One, I'll show a series that is bounded, and is monotonic. And the series of changes, I'll show a series. So the way the update goes is that we pick up a neuron in the network, and we check the sense of the neuron. It's called the sense. Basically, it's the combination, the linear combinations of the weights that are going into the neuron times the values of all the other neurons that are connected to that neuron. Typically, it's all of the neuron in the network. So that's the sense. We pick up randomly. We pick one neuron, and we see whether the sense is bigger than 0 or less than 0. I'm ignoring bias for now. And if it's bigger than 0, then I update the neuron to be 1. Otherwise, the neuron is still updated to 0, basically. So that's the update rule. And we need to convince ourselves that there's some, in order to see that the process converges to a fixed point, we need to convince ourselves that there's a monotonic series that is bounded, and that proves the claim. So what we have series is the energy that of the network. That's how it's called. It's called the energy. And basically, this is the sum of the weights on the edges times the values of the values that are of the neurons that are at the end of those edges. Okay, and because I'm randomly picking when I'm changing at each stage of the update, as I retrieve the element, I'm picking a neuron. Therefore, I chose L to be the neuron that I'm picking, and I separated the energy to the rest of the energy, which is not changing. I'm not changing it. And the part of the energy that has to do with the neuron that I'm updating. And now all I have to determine is whether my change to the energy is monotonic. So in this case, it's going to be monotonic decreasing. So there's two cases to consider. One is that the sense at the entrance to the neuron I'm focusing on is bigger or equal to 0. Okay? So in that case, if the neuron is 0, it stays 0. If the neuron is 1, it stays 1. Sorry, if this is strictly bigger than 0, then it will go to 1. If it was 1, it will stay 1. If it's equal to 0, then it will stay 0, if it was 0. In any case, it will either increase or stay the same. So what happens is that the product of these two things are positive, and the energy is negative or 0. Okay, so it decreases. Same case with in the case that this is that the sense is at the entrance to the neuron I picked is less than 0. Same case, same analysis. Again, the energy will go down. So what we see is the energy is going down at each update. In addition, the number of states in the network is finite. Do you see why? Why is the number of states in the network finite? So the weights are set, they are fixed, they are constant. And the neurons can have either a value of 0 or a value of 1. How many neurons do we have? Finite number of neurons, right? And everything is connected with everything. Then why is the number of states of the network finite?
You're saying because it has to be 2 to the number of
Exactly.
neurons? Okay, so that's
Exactly.
fine.
Yeah. And as a result, it's also bounded. The energy is also bounded. So essentially what we've seen here is that the process converges and converges to, and that's how the retrieval is done in the network. Any questions or thoughts about this? Okay. Okay. So yeah, thank you very much for joining today, and we'll continue next time.
Eitan, can you share a good summary of this paper? Because I think you've shared it with us privately, but yeah, the paper is like 90 something pages long.
That's true. So the thing to do with that paper is to not read the appendixes, okay? So if you just try and understand the claim, the mathematical claim, then you're okay. Understand what the claim is. You don't need to read the proofs, okay? Actually, I've seen a YouTube. You know what? I've seen a YouTube of the paper. I can send it to everyone. That would be interesting. may be helpful. Okay.
Yeah, I think it would be like I also need to maybe.
We can't hear you well, Axel.
Sorry. Yeah, I think it would be great to send a video on YouTube and also the link of the paper because
Okay.
we need.
Okay.
Thank you.
Yeah. I've seen. I'll send some videos. Okay.
Thank you very much.
Yeah.
Thank you, Ethan.
Thank you. To be continued.